Okay, what we want to talk about is really the subject of that problem, and that is 2 and 3 force members. Okay, and the reason why we want to identify 2 and 3 force members is because it helps us solve the problems a lot easier. If we don't see a 2 force member for what it is and a 3 force member for what it is, oftentimes that's the key component to solving something that we couldn't have solved before. Okay? And so let me show you first, go with the easier part, and let's talk about 2 force members. And trust me, this will lead to answering your question. So first talk about 2 force members. Okay? Basically, when we talk about 2 force members, don't think that a 2 force member is something like this. Okay? Don't think, well, this is 2 forces, and somebody might look at this, let's pretend those forces are at that point. Somebody might look at that and say, that's not a 2 force member, that's a 4 force member. No. That is a 2 force member because it's not how many forces you might see in a free body diagram, it's how many locations of forces. Okay? So that's a 2 force member that you have right there because you have forces only at locations, let's just call them A and B for this example. Okay? So that's a 2 force member. Okay? In fact, you might have a 2 force member like this little L joint or whatever like this, and you might put, and let's say it's pinned at A and it's pinned at B, and you might put the forces on there like this. And really there's nothing wrong with that. You'd say, let's just pretend. You say, oh, well, Dr. Reynolds, it's pinned at A, so I know when it's pinned I draw forces X and Y, and it's pinned at B and I draw forces X. Notice if it's pinned at A and B, you have 4 different unknowns now. But this is a 2 force member, so this is not as hard as you've made it to be. Okay? If you have a 2 force member, let me redraw here so we can see it better, and you only have forces at A and B, then there's something that you can do. Okay? And there's something that makes it special, and that is if you connect the line, just make a little dotted line here. If you connect the line between the points that have the 2 forces, A and B, you know for a 2 force member, the forces have to be either like this, equal and opposite right at each other, or they have to be the other way, like that. That's the only 2 cases you got. They either have to be coming in or going out, but they have to be parallel and collinear, okay? They have to be parallel and they have to be collinear on the same line. Now, some of you might say, prove to me that. Why do they have to be like that? Why couldn't they be something like this? I'm going to give you one more L beam. Okay. A, B. Why couldn't A, instead of being like that, why couldn't A be like this and B be like this? Why couldn't it be like that? Or let's give you another example. Why couldn't it be like this? Oops. Why couldn't it be like this and like this? Why does it have to be like the case you showed me, parallel and collinear? Why does it have to be like this, parallel and collinear? Why couldn't it be one's up, one's straight down, or one's at an angle this way and one's at an angle that way? Easy to prove. All you have to do is do moments. Ask yourself, take a look at this bottom picture that I've drawn. Ask yourself here at the bottom picture, what's the moments about A? Remember in statics, the moments of A have to equal 0, right? In statics, some of the moments about A has to equal 0. And also in statics, by the way, some of the moments about B has to equal 0, right? In statics, some of the moments about any point has to equal 0. So, if you choose A, for example, okay, if you use either the red case or the green case there, the moments about A have to equal 0. Well, the forces here go through A, right? But the forces at B don't go through A. Never be true, okay? The moment equation says this can't happen, okay? The only thing that can happen is right here. The forces have to be either equal and out. They have to be equal and opposite. They either have to be coming in towards each other or going out, okay? But they have to be along a line that connects AB. All right? That's two force members. And remember, it's locations. It has to have 2 points where forces are at. That's all it means. You could have components, but if it's 2 separate physical points where forces are at, and that's it, there's only 2 points that have forces, it's a two-force member. Okay? That is going to be really, really important when we get into bridge trusses. Okay? Because when you look at a bridge and the trusses that hold up a bridge, they're almost all two-force members. Okay? That's pretty much how we model them all. Okay? So we do a lot with two-force members. Okay? Makes it easy. Makes our life really, really easy. They have to be equal and opposite and collinear. Parallel. All right. What about three-force members? Oops, I can't spell. Okay. Let's use the same L-shaped bracket. Let's say it's got forces at A, it's got forces at B, but this time I'm going to actually include the weight force. I mean, every bracket has weight, so I'm going to say the weight is centered at this point G, and its weight force is like this, W. Okay? Now, let's also say that for some reason I know that the force at A, and maybe I know from looking at another object or something like that, but let's just say for some reason I know the force at A looks like this. Say I know that. This is the force that's at A, pulling this way on this L-shaped bracket. Okay. How do I know that? Well, maybe looking at the other piece that A is connected to, I figured out that that force has to be horizontal. I'm just coming up with an example. This works no matter what direction you have the force at A. But you have to have a certain direction for the force. Let's say you know there's that force at A like this, and this is now a three-force member. I can guarantee you that I know the direction of the force at B. The reason I can guarantee you that I know the direction of the force at B is that with a three-force member, all 3 lines of actions of the forces have to meet at a point. So what do I mean by the line of action? The line of action of FA would look like this, right? It's a horizontal line. The line of action of the weight force, obviously, is a vertical line like this. And the line of action of the force at B must be like this. Why? Because all 3 must meet at a point. All 3 lines of actions have to meet at a point. Do you know where that point is? Not necessarily, but they all have to meet at a point. Okay? All 3 lines of actions have to meet at a point. And if I happen to know that the force at A is horizontal, and I happen to know the force at G is vertical because it's a weight force that goes down, then I could guarantee you that the force at B has to go through that same point, whatever that point is. Okay? But that point there has to have all 3 forces go through it. Therefore, the force at B must be either like this, down, or possibly the opposite direction. I don't know which way it is necessarily, but I do know its line of action has to go through the point where the other 2 lines of action meet. All 3 have to go through the same point. How do I know that? Moments. Yeah, same reason. Let's pretend this point where they all meet is C. And let's pretend, for example, that the line of action of B is not like how I drew it, but is instead different. Let's just pretend for a moment that the line of action is somewhere else, maybe like this, or some other direction, right? Well, you know what? I'll use a different color. I think on here I can get away with a different color. So we can make this better. Look, I can change it to purple or something. Let's try that. Can I do purple? Hey, look at that. Sort of works. Okay, let's pretend it's like that. Or like this. Doesn't look too good. I don't know why. Okay, let's pretend it's not like I showed it. Okay? Let's pretend that the line of action is somewhere else. To prove that that purple one can't work, sum the moments about C. If you sum the moments about C, it has to equal 0. Okay? Sum of the moments... Oops, now I got this weird color. Got to get rid of it. That's too weird. Okay. Sum of the moments about C has to equal 0. But the force at A and the force at G already go through C. So those don't do any moment about C. Therefore, the only way this works is if the force at B forces have to come together at a point. Okay? They all have to come together. Okay? Now, that was a whole long thing I did plan on going into today because I wanted to talk with you a little bit about that before I showed you, or at least in context with, the problem. Okay? So now let's go take a look at this problem here. Okay. What it's saying here is that ABEF, which is a horizontal bar, ABEF, is one piece, and BCD, a vertical bar, is also one piece. And it asks you to look for the 2 and 3 force members. Okay? So for instance, bar DCB, which is the vertical bar, bar DCB is a 3 force member. How do I know it's a 3 force member? Because it's only connected at B, C, and D. B, C, D. That's 3 points, right? B, C, D, that's 3. So that's is there anything that's a 2 force member? Yes. FG. Bar FG is it's a curved bar, but it's still a bar. And it's connected at a force exists, F and G. All right? Since that's a 2 force member, I can tell you guaranteed where these forces are. They have to be either like this, coming together, or possibly the other way, going apart. But they have to be along that FG line. That's the only way for it to work. Okay? Now, another thing is, you don't have to just look at one piece. You could also look at the structure together as one body. If you look at this entire structure and pretend in your mind that it's just one body, then how many points are application of force on that? There's one, A, right? Where else is force applied on this thing? Where is it connected, basically? D, right? And G. You see that? If you look at this one piece together as one body, pretend it's one body, it's a 3 force member. It has forces at A, G, and D. That's it, right? Those are the only places there are force on this body. A, G, and D, if you consider it all one body. There's no other places where there could be force. It's a 3 force member. What do we say about 3 force members? All the forces have to come together at a point, right? But what do I know about the force at G? It looks like this. It has to be horizontal. So then what point must all the forces come together? If G is horizontal and P is vertical, what point must all 3 forces, A, G, D, come together? At A. See that? Because this one has to be horizontal. So you have to follow the line, go to A. P is a vertical. So they have to come together at A. So therefore, you know the force at D, where it goes. The force at D has to do that. Okay? So that's the beauty of a 3-force member. Once you see it as a 2-force member or a 3-force member, you know what it is. By the way, link CE in this picture. CE, that's a 2-force member. You can clearly see it's a 2-force member. There's only 2 points that has force on it, C and E. So you know those forces. They have to be along that line. Huh? That really helps you see it as you go on. It's really important to look for 2 and 3-force members. Makes life easy. You go, oh, I know what that is. I can see it already. Okay? Okay. Oh, okay. So I spent 20 minutes and I didn't answer your question. All right, well, how do I answer your question? Okay. Yeah. So, yeah, you need to solve for the forces at D and G, right? So, how do you solve for the, let's say, well, it does help to answer your question. It really does, because, let me bring this back up. Oh, here you go. Since you know, put it this way, since you know the force at G is horizontal, right? What if I sum moments about D? Sum moments about D here. It's between this horizontal force and D. Right? You know what that is. You know what A and D are. It's given to you in the problem. What's the perpendicular between the vertical force at A and D? Right here. See? Right? So it's easy. Some moments about D. You'll solve it. Okay? So that will answer your question. So, okay. All right. Good questions. Okay. Now we are going to get into the 3D world and talk about equilibrium in 3D. Okay? Let's see here. Okay. So what we got here is with 3D equilibrium problems, we actually have 6 equations. And you might look at this and say, oh, gee, I only see 4 equations. I don't see 6 equations. I see some force is x, some force is y, some force is z. That's 3 equations. And some moments about A, that's only 4 equations. I don't see 6 equations. But the thing is, you realize when you're in 3D, the moments is not just one equation now. Okay? When you say sum of the moments about A, and it doesn't have to be A, it can be any point, right? If you say sum of the moments about A is equal to 0, what you're really saying is sum of the moments about A is equal to a certain amount I plus a certain amount J plus a certain amount K, and those all have to equal 0. So all of the I moments have to equal 0, all the J moments have to equal 0, and all the K moments have to equal 0. See, it's 3D now. So you don't have just one moment equation. You have I, J, K moments. So that last one there, some of the moments about A, that's really 3 equations. I, J, K. So because we have 6 equations, we can solve up to 6 unknowns. That sounds fun, right? Oof. Now we got to do 6 equations, 6 unknown. Yeah, talk about a matrix. You're going to have a big matrix now. I want you to picture a 6 by 6 matrix with 36 different numbers in it. Yeah, that's what we're doing, okay? The good news is sometimes it's simpler than you think. And that sounds pretty messy, and it could be, but sometimes it's not so messy, okay? All right. Well, before we get into actually solving 6 by 6 matrices and doing all that fun stuff, we need to understand how to handle the supports, the reactions, to ground in 3D, okay? This is just like the chart I did last week in 2D, okay? This is straight from your textbook. There's nothing... Now, I'm going to show this to you. I'm going to explain this to you. But I'm going to tell you this. if you can understand the principle behind this, it's going to be a lot better than memorizing this chart. Okay? So let me start with the first few, because the first few are pretty easy. Okay, cable. Okay? Yeah, cable, we've been dealing with cables in 3D the whole semester almost. I mean, cables in 3D are no big deal. The reaction is a force. It has to pull, right? Cables always pull, and it has to act in the direction of the cable. That's easy. We've done that one, okay? So that one doesn't really change much in 3D. It's just a 3D cable now instead of 2D. Okay. Number two and number three are pretty much the same, right? 2 is a smooth surface support, and 3 is a roller. Okay? Basically, they're the same thing. Basically, if you have a roller or a smooth surface, the reaction is a force that's perpendicular to the surface at the point of contact. Okay? And so in this case, either one of them, now in 3D, you could have a 3D surface. I mean, the plane could be like skewed. It could be in who knows what direction, but it's a 3D. It's perpendicular to the surface. Okay? Those aren't too bad. All right, now let's get to the first new one we have, number 4. We've never dealt with this one before. Ball and socket. Ball and socket, the easiest way to image and imagine a ball and socket is think of your arm, okay? Your arm is like it, moves around, okay? And your shoulder is like a ball inside your socket joint, okay? So your body has a ball and socket joint with your arm, okay? And kind of like with your legs too, right? I mean, we could model your arms and your legs as ball and socket joints. The shoulders, basically, and your hips, okay, as ball and socket joints, okay? Is that a perfect model? No, but it gets the idea, okay? The idea is that your shoulder hopefully keeps your arm from separating from your body, right? And so your shoulder is modeled as a ball and socket joint because your arm can still rotate in any direction it wants. I mean, I can turn my arm. Okay, you can rotate it all sorts of different ways, but you cannot, hopefully, pull your arm out of your socket, right? We don't want that. So what happens is that the joint prevents forces. It has forces X, Y, and Z to prevent that motion. So there are forces to prevent that from happening, okay? But it has no moments. There are no moments there. You don't draw moments because, okay, turning. It can rotate freely, okay? And so you're going to see the ball and socket joint. It's very common. It's kind of analogous a little bit to a pin joint in 2D because all you have is forces X, Y, Z. That's all you have, okay? You don't have any different than is these bearings, okay? Now, bearings are very important in a lot of different applications, okay? Bearings come into play, all sorts of industry applications, all sorts of different consumer products, okay, things like that. I have got a stroller at home for my kids, and I'll tell you the difference between an expensive stroller that works well and a cheap stroller is almost always the bearings, okay? Because if you've ever dealt with this before, and maybe you haven't if you don't have kids, but if you have a good stroller that rolls real nice, it's because of the bearings. The bearings are good. The bearings roll freely and smoothly, okay? And we have an expensive stroller that the bearings are really nice, and that thing, you push it, and it goes real smooth. Then we got another cheap stroller with bad bearings. That thing is just so much harder to push because those bearings have a lot of friction, okay? So bearings are very important in industry. There are companies that focus all on bearings because their bearings are everywhere, okay? And so there are different types of bearings, and one of the most common is what's called a journal bearing, okay? And a journal bearing, basically, you have, in this case, you have a circular shaft in a circular hole, okay? So circle shaft and a circle hole. And so the bearing has certain reactions here, okay? Now, before I get into these reactions, I want to explain to you the principle, okay? Because, see, again, I don't want you to memorize this chart. You could if you want to, but I'd rather you not, okay? So what I'd rather you do is understand the principle, and that is this. I'm going to write this out here. If the support does not allow motion or rotation in a particular direction, then it will have a reaction force or moment in that direction. Okay? Okay? What does that mean? It means basically that if it doesn't allow motion in that way, then draw a force to prevent it. If it doesn't allow rotation in a certain direction, then draw a moment reaction to prevent it. Okay? Now, let's take a look at this example here, the journal bearing. Remember, we have a circular shaft in a circular hole. Okay? Circular shaft, circular hole. Now, it's a little hard to visualize probably by looking at the screen, probably a little bit easier to visualize by looking at the piece of paper that you have in front of you here, though I have to admit even that looks kind of small, which direction it is. The X direction is to the left, the Z direction is up, and the Y direction, by the way, here is parallel to the shaft. Okay, the Y direction is parallel to the shaft. Okay, so does this bearing prevent motion in the X direction? Can I just grab the bar and move it in the X direction, or does the bearing stop it? The bearing stops it, right? I can't just move it in the X direction. Therefore, I draw Fx as a reaction force. Could I grab the bar and just pull it up? No. Right out. There's nothing to keep it from pulling out, so that's why you don't put a force there. Okay? Same for moments. If I were to grab this thing and try to turn it around, circular shaft, circular hole, I could turn it. I could turn it that way. Sure. Okay? So, yes, that's why you do not have a reaction force in the Y direction. You do not have to understand the principle than to try to worry about understanding the every single 3-by diagram. Okay? All right. How about this next one? It's a single journal bearing with a square shaft. Okay, now, the only reason why you'd have a square shaft is to prevent the rotation. Because it's pretty hard to rotate something that's a square shaft in a square hole. Kind of hard to do that. So, therefore, the only difference between 5 on the last page and 6 on this page is you notice a reaction moment. It prevents rotation about the y-axis. Okay? So you have 5 unknowns. Okay? Now another one that's pretty popular is called a thrust bearing. Okay? Basically a thrust bearing has, when you put it together, the shaft is probably a little larger than the hole. And what it's called an interference fit. Okay? Interference fit means basically you're fitting something that's larger than the hole. Can you do that? Sure. You just have to force it in. You have to have a lot of extra force to make that happen. Okay? And so, yes, you can do that. You basically force it in, and so it's larger than the hole. Industrial system, one of the bearings will be a thrust bearing, because if none of them were thrust bearings, then the whole shaft could move. You wouldn't want that. Okay, so one of the bearings uses a thrust bearing that kind of holds it in place. Okay, in some kind of industrial line or system or whatever. Okay, so that's a thruster. So it has a force in the Y to keep it from moving. Okay, a smooth pin. Okay, a pin. Basically, a pin in 3D. Okay, in theory, you can't move with the object X, Y, or Z. So you have reaction forces X, Y, and Z. Okay, and you can only rotate it about the pin axis. Okay, you can't rotate the object off of other axes because that just it can't work. It would break the pin, right? You can only rotate the object about the pin axis, which in this case happens to be the x-axis. So you have a moment reaction about those axes. Okay, a hinge. Okay, just like this door. I mean, a very clear example is a door. Okay, you can only rotate the door turn it, you know, this way, just so there's only one way you can turn it, and that's the hinge axis. Therefore, you have reaction forces X, Y, Z, because I'm assuming I can't pull the door off the hinges, right? But I also can only turn it about the hinged axis. I can't turn it about any other axis. So you actually have 5 reactions here, okay? And then finally, the one that's the most unknowns is what's called the fixed support, okay? Basically, if it's fixed into the ground or whatever, like a tree, think of a tree in the ground, right? You can't pull it out X, Y, or Z, and you can't rotate it X, Y, or Z. Okay, so you have reactions in every direction. Okay, remember in this analysis, you can only solve for up to 6 unknowns. So if you have a fixed support, that's it. I mean, you can't solve anything else. If you have a fixed support, that's it. You have to have everything else known because you have 6 unknowns in a fixed support. Okay, that's all. That would be the only thing you could solve for. Okay. Any questions on that? Not that clear as mud? Okay. All right, let's do an example. And admittedly, these examples do take some time. Okay? Anything you do in 3D is going to probably take some time. Okay? And so these are going to be a little longer problems to solve. Okay? But they're, I think, more interesting because I think you can practically understand them. Okay, this is like a road sign or something like that, or some kind of sign. Maybe it'd be in front of a business. Maybe it'd be on the road, a traffic sign or something like that. Some kind of sign. And the sign weighs 50 pounds, and it's supported by the bar BD, which is hooked on to some kind of collar there at A. Okay? So that the blue part is basically also part of the whole sign mechanism. Okay? And the sign is attached to ground basically at 3 points. E and C, which are basically support cables. Okay, they go to E and C. And then what you have at A is what they call a smooth collar. Okay? So what we're going to do is draw a free-body diagram. Before I draw the free-body diagram, let me just explain that this problem can be a little bit difficult to visualize. When you look at this sign, okay, that sign is below the XY plane. Okay? Some of you will stare at that sign and go, I have no idea how that sign could be below the XY plane. It sure looks to me above the XY plane. Because if you look at the bottom of the sign, what you'll do in your mind when you see the y-axis and the bottom of the sign is you'll visualize that sign above the XY plane. That sign is actually below the XY plane. Okay? It looks a little weird. When you stare at it, you're like, hold on, no, that sign. point B there, okay, is actually to the right. It's actually in the negative x side, okay, to the right of y, okay? And so, and G is actually a little bit to the left of the y-axis in the positive x direction. Hard to visualize, I realize that, because a lot of people look at that sign and think it's above the plane. It's actually below the plane, okay? So once you see it, you go, okay, yeah, I see. It's just, I think it's because the y-axis comes all the way out. You want to visualize it. If they would have stopped the y-axis earlier drawing it, I think it would have been easier to see. In your mind, don't put the y, you just kind of stop it there and go, oh, okay. So that line that runs from A on the y-axis, that's right from the origin. A is at the origin there, okay? And it goes down. The sign goes down below, okay? I want to start that now because everybody, like 5 minutes later, go, I don't understand why you're getting that. So, okay, let's draw a free body diagram of this thing. Now, normally, I don't recommend drawing free body diagrams right on the figure. But let me tell you, I stink so bad drawing 3D, and I think you're going to get more confused if I don't. So I'm going to draw this free body diagram on the figure. Normally, I won't do this, but I think in this case it calls for it. All right, so let's do the easiest thing first. I think you all agree. 50-pound sign at G, we're going to draw like that. Okay. Weight force always down at G, there it is, 50 pounds. Now, how about D to E and B to C? Those are both cables, right? Cables always pull, so I'm going to draw it like this. I'm going to draw a pull, and I'm going to call it F, D, E. And I'm going to draw this one a pull. I'm going to call it F, B, C. You can call it whatever you want. That's what I call it. Okay? I'm drawing a free body diagram, by the way, of the sign plus its bracket. Okay, sign and bracket. Not just the sign itself. The sign is in the picture is brown. It's not just the brown sign, but the sign and the bracket. Okay? So what's going on in A? Okay, I think what's going on in A is a very good way to understand the principle of how I draw what forces do I draw at A? What moments do I draw at A? What do I draw at A? Okay, understanding what you draw at A will help us. Okay. Everybody look at that collar at A, that support at A. Look at the picture or look at it on your paper. Okay. Does this collar prevent the sign from moving in the X direction? Could I just grab the sign in the bracket and pull it in the X direction? Don't worry about the cables. Don't even think about the cables. Pretend the cables are cut. Could I just, does the collar prevent me from moving? Yes or no? Could I pull the sign, or would the collar keep me from doing it? Would it keep it in place? Keep it in place. Everybody. Pretend like it's like absolutely can never break. It's made out of super titanium. Okay, it never breaks. So could I move this in the X direction? No, I can't. Okay. Therefore, what do I draw? I draw AX. I draw a reaction force AX. Because there's a reaction force at A in the X direction that prevents that motion. That make sense? Thing for Y. Could I grab that sign and pull it straight out in the Y direction? Or does the support keep me from doing it? Direction. Therefore, I better draw an AY. Okay? How about the Z? Don't look at the cables, cut the cables, forget them. Look at just the support. Could I move the sign up and down and slide it on that pole? Of course I could. So there's no force in the Z there. There's no force in the Z. I don't draw an AZ because the support does not prevent that motion. Okay? The support says, sure, you can slide up and down, so I don't put a force there. Don't touch it. Okay, because it doesn't do anything to prevent that. Okay? Now, let's do the harder part. The harder part's moments. Okay? What about in the moment about the x direction? Does that collar there prevent me from rotating the sign around the x-axis? Kind of have to look at the side view and kind of try to rotate it. Does that collar keep me from rotating it? Yeah, yeah. So I have to draw a reaction moment about the x-axis. Here's how I'm going to draw it. Use a different color. Call it MX, like that. Note I drew it positively. So how do I know I drew it positively? I use the right-hand rule. Put your thumb in the direction of the positive x-axis. Your fingers will curl in the positive moment direction. Okay, so that's a positive moment at x. Do you have to draw the positive moment at x? No, you really don't, but I just normally do. Okay? Okay, how about the support? Does it prevent me from rotating it about the y-axis? Could I take this sign and pretend like it's a steering wheel and turn it around the y-axis? Nope. Nope, can't do that either. So I'm going to draw a positive reaction moment my. Okay, like that. Might be hard to see, but basically I just draw like a little curve there. Another way sometimes people draw this. Let's take a look just at the x. Some people will draw it like this. Some people draw the ax like this, and they'll draw the mx like this, the reaction moment like this, with a double arrowhead. And sometimes I might do that as well, because sometimes it's cleaner. Instead of trying to draw those little circles in 3D, the little curves, you can just draw AX and an MX. And if you use the double arrowhead, that's kind of a convention for moment. Okay? So sometimes we draw it like that. In this case, I drew them as little the green with the curves because I kind of... Okay. Lastly, the moment about the z-axis. Forget the cables. Could I spin this thing around the pole? Of course I could. So do not draw a moment about the z. In fact, I've drawn everything I need. I believe I have a complete free body diagram. One thing you can do, double check this. You can't have more than 6 unknowns. You can't have more than 6 unknowns. My unknowns here are FDE, FBC, AX, AY, MX, MY. 6. So I can solve this. Okay, how do I get to the actual mechanics of solving it? Well, all you got to do, some forces x equals 0, some forces y equals 0, some forces z equals 0, and some moment about some point equals 0. You got to solve those 4 equations. Once you do the free body diagram, you solve those equations. That's all you have to do. Of course, the devil's in the details. It's not always as easy as it looks. But that's it. Write the free body diagram, solve those equations. Okay? Now, let's do that. Let's get started on this. Okay? And let's get into that. And we probably won't solve it all today. Okay? Some of these problems, 6 equations, 6 unknown. That's messy. On a test, I might not actually ask you to solve it. Or maybe I will. It depends on how hard it is. And how much time I think you're going to need to do it. But sometimes on a test, what I might ask you to do is just write the 6 equations, 6 unknown. Just write them out. Solving it, that's another step that maybe takes too much time. Okay? Though honestly, if you put it in a matrix, it doesn't take that much time. Okay? Okay? So how do we do this? Well, what you got to do, the only thing you got to really do here before you solve it is you've got to take FDE, the 2 cables there, DE and BC, and you've got to break them up in IJK. Just like what we did 6 weeks ago, right, when we started learning about this, we just break things up X, Y, Z from forces, cables that are in 3D, right? We've been doing this a long time, so this is not new. But it may be a little tricky to visualize. If you go from, let's take a look at DE, the force DE. If you go from D to E in this picture, what are you doing? This gets a little tricky in terms of I, J, K. If you walk from D to E, how is that going in the X direction? 1 foot, you see that? Because point D is 3 feet from the y-axis, and point E from D to E, it's 1 I. What about the J? How far back are you going in the Y? 2 feet. How about the K? How much up are you going from D to E? 2. Yep, 2. Okay. Now, again, reminder, you make the unit vector in the DE direction. That's 1I plus 2j plus 2k, all divided by the square root of 1 squared plus 2 squared plus 2 squared, which that's a nice one because the bottom is the square root of 9. The square root of 9 is 3, right? So you can write the force FDE as a vector. It's equal to the scalar FDE times 1/3 I plus 2/3 J plus 2/3 K. That's nothing new. I'm assuming you can do that. In the same manner, I'll go quickly here. You can do the same thing with the force BC. If you go from B to C in your picture, if you look at it carefully, you're going minus 1I minus 2J plus 2K from B to C. Therefore, I can write out the force BC as a vector. It's equal to FBC as a scalar times minus 1/3 I minus 2/3 J plus 2/3 K. Hopefully by now you know how to do that, because we've done that quite a few times. Okay?
DE, would that be a minus 2/3 J because it's going backwards to
Yeah. Yeah, you're right. Sorry. That's minus. You're right. That's a minus. It's minus 2. Yeah, minus. You're right. So it's all minus. Yeah. Easily correctable on mine. I got a little eraser. You're right. Yeah, they're both going backwards in the Y, so they're both minus in the J. Yes. Good. Thank you. Okay, so this first part's really easy. The force equations, everybody should be able to do this. Okay? This is easy. Sum of the forces in the x direction equals 0, where the x direction is positive like that, down and to the left, right? So, what forces do I have in the x direction? Well, it's the forces that are in the I direction, right? So, what do I got? Well, I've got 1/3 FDE in the I direction, right? 1/3 FDE. What else do I have in the I direction? Well, I have minus 1/3 FBC. Okay. And if you look at my free body diagram, is there anything else that's in the x direction? AX, that's right, the reaction force at A, AX. So I simply do this, plus AX equals 0. That's the only three forces I have in the x direction. The cables both have forces in the x direction, and then there's a reaction force at A. That's it. Those are the only forces in the x direction. So that's one equation. Okay? Now you do the same thing for the y. Some of the forces in the y direction equals 0, down and to the right, positive. If you look at the j terms of your cables, right, you get minus 2/3 FDE minus 2/3 FBC. And then the only other term you have in the j is, or the y direction, same thing, is AY, right? And that's equal to 0. That's not in the y. We're getting there. It's not there. Okay. Then finally, for the forces, sum of forces in the z direction, up positive, equals 0. You've got 2/3 FDE. You got plus 2/3 FBC. Those are both in the K, right, Z. You do not have a reaction force at A in the Z direction, but you do have the weight force. So you have minus 50 pounds equals 0. It'd be really great if we could just stop here, because this would be nice. But unfortunately, I only have 3 equations and I have 4 unknowns. I can't solve this. Because my unknowns are the forces in the cables, FDE and FBC, and in this case, AX and AY. A moment equation. And the moment equations, unfortunately, are painful because they're long and messy and involve cross products. Now, you don't have to do cross products, but with 3D, I recommend them. Because in 3D, it's hard to visualize without cross products. But if you wanted to, you could do like what I did last time, and you could try to draw 3 different views of this object and try to work it all together, but it gets really messy. I think it's probably the easiest is to draw cross products, okay? Unfortunately, there's no way around it. This is messy, okay? And so this last equation I'm going to write is extremely long and messy, okay? Well, I mean, in my perspective, it's not extremely long. I once had an equation that took 26 pages to print out, okay? But, you know, in your perspective, this is extremely long and messy, okay? So, yeah. So, this still will look messy and bad, okay? You won't like this equation. You will be unhappy when you see this equation. You'll be like, oh no, I have to deal with stuff like this. Hopefully it won't be too bad. Okay, all right. But this will not make you happy. Unless you like lots of cross products and messy equations. Some of you do. Some of you will be happy when you see this. I will say that. But most of you will not be. It will either way, it will have a lot of emotion attached to it. Okay. All right. So what do you got to do? Well, you got to do moments, right? You got to do moments. So we got to ask ourselves, some of the moments about some point, it doesn't matter what point you pick, is equal to 0. What point would you like to do moments about? Usually you pick a point where a lot of unknown forces come together. That's A. Some people might argue and say, I think it's easier to do D or B because then I don't have to worry about one of those cables and then the other cable is very simple because the radius, the R to that is very simple. You could make an argument that D or B might be easier, but I think A is probably the easiest in this case. On a test, don't overthink this. Just pick a point and go with it. But do try to pick a point where lots of things are coming together. In this case, A is a good place. Lots of things are coming together at A. So I would pick A. All right. So there's some moments about A equals 0. And because you're in 3D, you're probably going to want to do cross products. The two hardest ones to deal with are those cables, okay? And their moments about A. Remember that when you're doing moments in 3D, we're going to do R cross F, where R goes from the point you're doing moments about to any point on the line of action of the force, okay? I think in this case, the easiest way to do it is to do an R from A. I'm going to try to draw this in blue, and I hope this doesn't get too messy. But I like this R. From A to E. You can do from A to any point on the line of action of the force. Well, E is on the line of action of the force, so why don't you do an R from A to E? Seems to be pretty easy, right? So if you do an R from A to E like I have there on that blue vector, it's actually a really simple vector. It's 4I plus 2K. 4I plus 2K is from A to E, right? So you're going to do R cross F. Now F is that vector from D to E, okay? So this is a messy cross product. I mean, I'm not going to write it all out just yet, but yeah, it's messy. Okay, here we go. I'm going to write it down. I'm just going to write out the pieces first. This is going to be 4I plus 2K. Yeah, if you have your calculators, you can do this in your calculators. Crossed with FDE. FDE is 1/3 FDEI minus 2/3 FDEJ plus 2/3 FDEK. That's one cross product, but there's more.
Why
Yeah.
are we using the unit vector for the FTE and not just the force separation?
It's not the unit vector. It is the force vector. Yeah. Notice what I have here in blue, underlined in blue, FDE. I just put FDE in each one. That is not a unit vector because FDE is unknown force. So it could be 100, it could be 1,000, it could be whatever. But the only way it'd be a unit vector is if it so happened that FDE was equal to 1. But it's not. FDE is whatever it is. Yeah. FDE is 8 or 800 or 27,000, I don't know. But it's not 1 probably. So this is not a unit vector, most likely. There's certainly no assumption that it is. It's not. It's just the force. It looks kind of like a unit vector, but it's not. Okay, that's only the first cross product. We also have to add to it the other force, the other cable, right? If you look here, the other cable is an R that goes from A up here to C, and this RAC, if you work it out, is minus 3I plus 2K. Okay? Minus 3I plus 2K from A to C. Because you're going from A to any point on the line of action of the force. So this is what it looks like. It looks like minus 3I plus 2K crossed with, this is now the force from B to C, FBC. This is minus 1/3 FBCI minus 2/3 FBCJ plus 2/3 FBCK. Okay? So that's the two forces. Both those forces create moment about A. But there's also one more thing, one other force there that creates moment about A. It's not AX and AY, right? Because AX and AY go through A. What's the other force that creates moment about A in the picture? The load, the 50 pounds, right? The 50 pounds also creates a moment about A. If you take a look, that 50 pounds also creates a moment about A. So what's its moment about A? Well, you have to do R cross F again, right? And R goes from A to G. If you go from A to G, and I'm not going to draw the line because it gets messy, but if you go from A to G, you get the following vector. 0.5I plus 2j minus 1k, all crossed with minus 50k, which is what that force, that's the weight. Okay. So that comes from the weight force. That last term there, I'll underline it in red. That comes from the weight force. And I'm still not done, but I'm almost done. There's two more things that create moment about A. The reaction moments at A. Okay? If you look at your pre-buy diagram there, there's two other things that create moment about A. I have them drawn in green there. The reaction moments MX and MY. Okay? So you can't forget about those either. That's it. Then you got MX in the I direction, because there are moments about I, X, so the I, right? Plus MYJ, and that equals 0. And finally, okay. Now, on a test, if I said, give me the 6 equation, 6 unknown to set this all up, you really wouldn't be done yet. Some students get confused. They think that this is all they need to do. This is not the 6 equation, 6 unknown yet. You have to do the cross products. You have to do the cross products, and then you have to gather up all your I's, J's, and K's. We haven't done any of that yet. Okay? So you have to do all those cross products. I'm not going to do that right now. Okay? What we're going to do is when I come back, I'm going to show you, I'm going to step ahead and show you how that all looks. I'll do all those cross products for you. Okay? And then group them all together, I, J, K. And then, once you have your 6 equation, 6 unknown, you have to put in a matrix to solve it. Okay? Probably. I mean, you don't have to. You could do substitution, but it's going to take a long time. Okay? All right. So the good news, it doesn't get much messier than this. Okay? I promise you. It's not like a month from now we're at 16 equations, 16 unknown or something like that. This is pretty much it. So, and most of the time we can make simplifications to make it easier. Okay?